Hello, and welcome to my presentation on engineering biodegradable components for packaging digitalization. First of all, let me present our team. So, this is a digital future research pair project in collaboration with me at Nanobiotechnology and SciLife Lab and Tiziana Fuoco at Fiber and Polymer Technology. And the students involved in the project are Yun Fan Lin and Max Hirschman. And the problem that we want to tackle in this project is food waste. If we look at Sweden, yearly we waste so much food that we could fill the Avicii Arena 4 times over. And if we look at the metrics for only 2018, 133 kilograms of food were wasted per person, which nationally it builds up to 1.3 million tons of food wasted in a year. And in US, the situation is not much better, with 1/3 of the food produced that is never eaten. And what happened to the food that is wasted? Well, it's incinerated or landfilled. And the problem is not only with the food that is wasted, but also with the amount of energies that are used in order to produce the food, which account into greenhouse gas emission, which is enough water and energy to supply more than 50 million homes. And also the amount of fertilizer that is used to grow all the plant-based food for human consumption, which in US basically accounts for an area of agricultural land equal to California and New York. But if we look back at our situation in Sweden, so we see that 20 to 25% of Sweden's total climate impact can be traced back to the waste of food. And where is the food loss? So food loss can happen at different stages of the food supply chain, from production to storage, processing, distribution, and eventually consumer losses. And if we look at the percentage, we see that overall, most of the food is lost at the consumer side. And why is this food lost? This can be due to a variety of reasons, from contamination and damages from inadequate safety controls, overstocking. We stock our fridge. We think our products are going to last for 2 weeks, but some of them expire. Inappropriate labeling, or maybe product information missing. And smart packaging has been introduced in order to provide a way to sense, monitor, record, trace, and provide information about the quality of food. And what it basically is a packaging system with an embedded sensing technology. And this should enable basically tracing the food products from production to consumption. For the producers, this will enable real-time monitor of the goodness of food and also quality control close to production. While for the consumers, it will provide a way to alert over spoilage and overall reduce waste. And in order to sense if the food is good or not, one thing that one can do is to develop an electrochemical biosensor. This is a technology which basically exploits a recognition element, a transducer, and basically a signal processor, which can provide us information, for example, to our phone. And the first important thing while designing a sensor is to define what kind of analyte do we need to sense. And for food, there can be a variety of analytes, from pathogens, toxins, metabolites. But in our project, we decided to focus on meat, which is one of the most energy consuming food. And we decided to focus on ATP degradation products as the analyte of interest. ATP is a molecule that is naturally present in muscle, for example, and it provides the source of energy needed for muscle to contract. But post-mortem, ATP is degraded by glycolysis into several products, among which hypoxanthine, xanthine, and uric acid. And in this project, we decided to choose this product because they have been marked or proposed as a suitable marker for meat spoilage. And in particular, we decided to start to develop a sensor for the monitoring of xanthine, possibly then extending to other products. And as a biorecognition element for our sensor, we use xanthine oxidase. Xanthine oxidase is an enzyme which selectively oxidizes xanthine to uric acid, and it generates hydrogen peroxide, which can then be sensed on our electrode surface. And our transducer in this case is a conjugated polymer on an electrode. And the conjugated polymers are a bit of special molecules in a way because they present all the properties of polymers, but in addition they have a conjugated structure, meaning the alternation of single and double bond, which give rise to what is called mixed ionic and electronic conductivity. And then we use this conjugated polymer on a working electrode as our transducer. And we inserted this in what is called a standard 3-electrode setup with a working electrode connected to a reference and counter in contact with an electrolyte. And we did some studies where we added increasing amount of xanthine, and we tested the response on the sensor current. And we saw that at potential between 0.7 and 0.8 volt, we have a change, which can then be plotted to form a calibration curve. So the calibration curve tells us basically how the sensor change for increasing concentration of xanthine, and but also for this particular kind of analyte, what we need is sub-micromolar concentration. So we want to move towards device geometry that is portable, can be integrated in packaging, but it's also sensitive enough to measure at very, very low concentrations. And then is when we decide to focus on a type of device called organic electrochemical transistor. So this is a 3-terminal device which uses a conjugated polymer as a core component in contact with an electrolyte. And basically what happens is that this kind of device uses the mixed ionic electronic conductivity of conjugated polymer to transduce ionic to electronic signal. And the electrolyte in our case is the liquid containing our analyte of interest. And as you can see, this kind of device has been used for several applications, including biosensors. And the aim actually of our project is not only to develop a biosensor, but to include biodegradable components in order to develop a fully biodegradable sensor. The idea is to integrate materials that provide high performance and stable operation during service lifetime, but also control biodegradation and a device that integrates into life and environment after disposal. And in order to develop this sensor, we started focusing on the substrate, which needs to be provide stable device support in contact with aqueous electrolytes. For that, we focus on polytrimethylene carbonate and polyhydroxyalkanoates, which are stable in contact with water, but degrade by the action of enzyme. And we started with the synthesis of this material, and we are looking into the effect of cross-linking on the density of the material, the stability during device fabrication, but also biodegradation time. And another important and challenging aspect for this kind of sensor is the electronic components, which can be, in general, they have been classified as partially degradable or completely degradable. However, all the materials that are completely degradable produced so far actually degrade via hydrolysis in contact with an aqueous electrolyte. Something that cannot work with our sensor. So one aspect that we are working on is actually to develop enzymatically degradable conjugated polymer and degradable contacts that we could integrate with the substrate components to provide a device that is durable in contact with aqueous electrolytes, but can also be biodegraded after disposal. This is an overview of our project, where we integrate aspects of material synthesis, fabrication, and sensing in order to achieve biodegradable smart packaging, but also with the aim to integrate sustainable materials and processes into the device design. Thank you very much for listening, and if you have any question, feel free to contact me.